Assignment 10 is very important. A new concept of invertible matrix is there for the basis of V, right? So it is written that columns of invertible n by n matrix forms basis for f n by 1 column matrices. If you look at here, this f n by 1, what does this mean? This n denotes the number of rows and this 1 denotes the column, right? So number of column is 1 only, single column, and number of rows are n, right? And only 1 column, which means it is a matrix having number of rows n but only 1 column, right? So it is a column matrix. It is a column matrix. So the columns of invertible n by n matrix forms basis for these column matrices. This is the space, like V is a vector space. So this is your space having f n by 1 column matrices. This we need to show, right? Okay, the complete example is, let P be an invertible n by n matrix. Now what is the invertible matrix? Whose inverse, the matrix whose inverse exists, right? So let P be an invertible n by n matrix with entries in the field F, then P1, P2, Pn, the columns of P. If P is your invertible matrix, then P1, P2, Pn denotes the columns of P, because it is n by n invertible matrix, which means it is having number of rows n and number of columns are also equal to n, right? So P1, P2, Pn, this denotes the columns, P1, P2, P3, Pn, so on. So these are the columns, right? So I have to show that these columns of P forms the basis for the space of column matrices f n by n. So what kind of space I am having? F n by n, the column matrices having f n by 1, which means the matrix having number of rows n and only 1 column. So these P1, P2, P3, Pn, the columns of invertible matrix P, forms the basis for vector space V, or the space having these column matrices, right? So let me erase this. Let's start with the proof. Let P denotes the columns P1, P2, P3 up to Pn, right? So let's take the linear combinations, right? So I'm taking x1 P1 plus this is x2 P2 plus x3 P3 plus so on xn Pn equal to 0, right? Then this can be written as in matrix form P1, P2, so on Pn multiplied with this x1, x2, x3, so on xn. If you multiply these two, you will get back the above equation. So this is equal to 0, right? Okay, this complete is your P and this is your x. So can I write Px is equal to 0? Px is equal to 0, where I'm taking x to be equal to, let me write this again, x1, x2, x3, so on xn, right? Okay, now because P is your invertible matrix, which means its inverse exists, which means P inverse exists. So can I multiply P inverse both the sides? Yes, I can. So this implies P inverse Px is equal to P inverse 0. So this implies P inverse P taking these two and this x is equal to 0. So this is nothing but your identity matrix, Ix is equal to 0. So this implies x is equal to 0, which means x1, x2, x3, so on, xn is equal to 0, which means each x1, x2, x3, so on are equal to 0. So x1 equal to x2 equal to x3 equal to x4, so on, equal to xn, all these are equal to 0. So if you look at your linear combinations, I'm having the columns p1, p2, p3, pn, and there's all the scalars are now equal to 0, which means it is proved now that p1, p2, p3, pn are linearly independent. Yes, it is proved. So therefore p1, p2, pn, all these are linearly independent columns. So first way is done. First condition is proved. Now second, I have to take one column matrix from Fn by 1, the space, and I have to prove that that matrix is linear combinations of p1, p2, pn, right? Then only I can say that p1, p2, p3, pn are the generators of Fn by 1, the generators of the space of column matrices. Okay, so let me choose one column matrix from Fn by 1. So let this be any column matrix, right? Okay, if x is equal to p inverse y, where x is equal to this, you know, then let me multiply p on both the sides. So this is px is equal, please just remember this, that we have taken x to be equal to p inverse y. P is an invertible matrix, so this exists. So px is equal to p inverse y, right? So this is equal to p inverse y. This is equal to identity matrix y, so this is equal to y. Sorry, I'm writing y like this. It's y only, right? So this implies this y is equal to px. See, px is equal to y. Can I write this y is equal to px? Yes. Now what is p? I know that p1, p2, p3 up to pn, right? And x I'm writing like this, x1, x2 up to xn. So if I multiply these matrices, so I can have p1x1 plus p2x2 plus p3x3 up to so on pnxn. Yes, which means this y which I have chosen from Fn by 1, this y is now the linear combinations of p1, p2, p3, pn. Yes, and because this y was arbitrary, which means every element of Fn by 1 is a linear combinations of these column matrices, of these columns. Yes, thus Fn by 1 is generated by p1, p2, pn columns, right? So from 1 and 2 I can say that because p1, p2, pn are linearly independent, and these are also the, now we have proved that these are also the generators of Fn by 1, right? So from 1 and 2 we say that these p1, p2, p3, pn forms basis for Fn by 1 column matrices, right? Okay, thank you so much. God bless you all.